Picture this. You're in a geography class. The teacher unrolls a world map across the board. The big one, the kind with slightly faded colors and a suspiciously optimistic depiction of national borders, and asks the class a question that nobody has ever thought to ask before. Why is almost all the land up here? And they gesture at the top half of the map. Europe, Asia, North America, filling the northern portion with comfortable density. Then they drag their hand down to the southern half, where the land masses thin out dramatically. South America tapering to a frozen point, Africa doing the same, Australia sitting in isolated mid-ocean defiance, and Antarctica at the bottom. Technically land, but buried under ice, thick enough to make it largely irrelevant to human civilization. The class stares. Someone in the back is still thinking about lunch, but if you actually look at the map, really look at it with the question in mind, something clicks that you can never quite unclick afterward. The planet's land distribution is not symmetric. It is not random. It is dramatically, conspicuously lopsided in a way that has had cascading consequences for every civilization that has ever existed, every trade route ever sailed, every agricultural system ever developed, and the entire trajectory of human history. And almost nobody has ever stopped to wonder why. So wonder about it now. Because the answer involves plate tectonics, planetary physics, deep geological time, and one of the most consequential geographic accidents in the history of complex life on Earth. Start with the numbers, because they're more striking than most people expect. Approximately 68% of Earth's total land area sits in the Northern Hemisphere. The remaining 32% is in the south. That's not a slight lean. That's a 2-to-1 ratio of land between the planet's two halves, and when you look at where the major land masses are specifically concentrated, the asymmetry becomes even more pronounced. Europe, Asia, and North America together comprise the bulk of the northern landmass, sitting in a rough arc that covers an enormous latitudinal range from tropical to polar. In the southern hemisphere, the primary landmasses, South America, Africa, and Australia, are smaller, more dispersed, and all taper or terminate before reaching the mid-southern latitudes where equivalent northern land continues existing comfortably. The southern hemisphere is, at a basic level, a water planet. Roughly 81% of the southern hemisphere's surface is ocean. The Pacific alone, in its southern extent, is a body of water so vast that the entire land area of the Earth could fit inside it with room to spare. If you're standing at the South Pole and spinning slowly, every direction you look is eventually ocean. The same exercise at the North Pole gives you the Arctic Ocean, but surrounded by the landmasses of North America, Europe, and Asia within relatively reachable distance. This asymmetry isn't an optical illusion produced by the Mercator projection, which famously distorts land areas toward the poles. Equal area projections, maps that accurately represent the relative sizes of land masses, show the same fundamental imbalance. The Northern Hemisphere simply has more land. The question is why? The answer begins approximately 4.5 billion years ago, and it requires briefly accepting that the planet's surface is not fixed, not even slightly. Earth's crust is broken into a series of tectonic plates, enormous slabs of rock ranging from thin oceanic crust to thick continental crust that move continuously across the planet's surface, driven by convection currents in the semi-molten mantle beneath them. The movement is slow by human standards, roughly the rate at which fingernails grow, but over geological timescales of tens and hundreds of millions of years, the cumulative displacement is enormous. Plates collide, producing mountain ranges. They separate, producing oceanic rifts and new seafloor. They slide past each other, producing fault lines. And they carry the continents around the planet's surface like passengers on very slow, very punctual trains to nowhere in particular. This process, plate tectonics, means that the configuration of land masses on Earth's surface is not permanent. It never has been. The map you're familiar with, the one from the geography classroom, represents one snapshot in a 4 billion year motion picture of continental drift. The continents have been in radically different positions at different points in Earth's history, and the current northern concentration of land is the result of geological events producing a configuration, not an eternal physical truth about the planet. For much of Earth's history, the land distribution was dramatically different. During the early Paleozoic era, roughly 500 million years ago, most of the world's landmass was actually concentrated in the Southern Hemisphere, in and around what is now the South Pole. A supercontinent called Gondwana, comprising what would eventually become South America, Africa, Antarctica, Australia, India, and the Arabian Peninsula, sat in the southern high latitudes, while smaller landmasses drifted across the equatorial and northern regions. The current northern bias is not an eternal feature. It's relatively recent in geological terms. Understanding how the current configuration emerged requires following the geological narrative through several hundred million years of continental motion, which sounds exhausting but produces results worth the journey. Approximately 300 million years ago, most of Earth's landmass had assembled into a single supercontinent called Pangaea, from the Greek for all Earth, sitting roughly centered on the equator and extending toward both poles. This was not an evenly distributed supercontinent. Even within Pangaea, the northern and southern portion, called Laurasia and Gondwana respectively, had distinct geological identities reflecting their different histories before assembly. When Pangaea began breaking apart roughly 200 million years ago, it didn't fragment symmetrically. The rifting began along lines determined by the underlying structure of the mantle, the weaknesses in the crust, and the pattern of convection driving the separation. Laurasia, the northern portion, comprising what would become North America, Europe, and Asia, broke apart and drifted primarily northward and eastward. Gondwana, the southern portion, fragmented into its constituent pieces and drifted in various directions, but the critical point is that Antarctica separated from the other Gondwanan fragments and migrated to its current polar position, while the other southern landmasses drifted to their current positions. The result of this fragmentation pattern was a northern cluster of landmasses that remained relatively connected or in close proximity. The Atlantic opened, but North America and Europe/Asia remained at similar latitudes, and Asia remained the largest continuous landmass on Earth, while the southern fragments dispersed into the water-dominated hemisphere they currently occupy. Antarctica's polar migration is particularly significant because it removed an enormous landmass from the temperate and habitable zone and placed it at the South Pole, where it accumulated an ice sheet that has persisted for approximately 34 million years. Antarctica is actually a continent of substantial size, roughly 14 million square kilometers, comparable to Europe, but it contributes essentially nothing to habitable land area because it's buried under ice averaging over 2 kilometers thick. If Antarctica occupied the same latitude as, say, Australia, the Southern Hemisphere land balance would look meaningfully different. The mantle convection patterns driving these movements are the underlying physical mechanism, and they reveal something important about why the asymmetry has been persistent rather than self-correcting. Earth's interior is not uniform. The heat distribution within the mantle, which drives the convection cells that move tectonic plates, is influenced by the distribution of radioactive elements producing that heat and by the pattern of heat loss at the surface. Continental crust, which is thicker and less dense than oceanic crust, insulates the mantle beneath it more effectively than thin oceanic crust does. This creates a feedback. Where continents cluster, the mantle beneath them heats up more, eventually driving convective upwelling that can break the continent apart, which is how supercontinents like Pangaea eventually fragment. But the breakup pattern of supercontinents isn't random. The upwelling that drives rifting tends to occur at specific locations determined by the thermal structure of the mantle, and the resulting fragmentation produces daughter land masses that drift in directions determined by the plate tectonics that follow. The current concentration of land masses in the Northern Hemisphere reflects the specific rifting geometry of Pangaea's breakup and the subsequent drift trajectories, and models of mantle dynamics suggest that the current configuration isn't simply a passing phase. The mantle's large-scale structure, including what's called the African superswell and the Pacific large low-shear velocity provinces, which are enormous thermochemical anomalies in the deep mantle, influences where upwelling occurs and consequently where continental material tends to cluster over geological time. The current northern bias in land distribution has been developing for roughly 200 million years and will continue changing over the next hundreds of millions of years as plate motion continues. Projections of future continental configuration, which are genuinely possible to model from current plate velocities and mantle structure, suggest another supercontinent assembly approximately 200 to 300 million years from now. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Though which configuration it takes is a subject of active scientific debate. The asymmetry has a second contributing factor that operates on top of the tectonic explanation. The difference in what happens at the two poles. The South Pole sits on a landmass. Antarctica is a continent with bedrock beneath the ice, and that bedrock is above sea level across most of its extent. The North Pole, by contrast, sits in the middle of an ocean. The Arctic Ocean, covered by sea ice, but underlain by water, up to 4 kilometers deep. There is no land at the North Pole. None. This polar asymmetry matters for land distribution because it means that the highest southern latitudes are occupied by a continent that contributes no habitable area, while the highest northern latitudes are open ocean. But the land masses just south of the Arctic Ocean extend well into the high north and include significant habitable area. Siberia, northern Canada, Scandinavia, and Alaska all extend to latitudes equivalent to Antarctica's outer margins, but those areas are land, not ice-covered polar continent. The presence of Antarctica at the South Pole is itself a product of plate tectonic history. It drifted into its polar position, and then, once there, developed the conditions that maintained its ice sheet. When Antarctica first migrated to its current polar position, it wasn't immediately glaciated. The ice sheet developed after the Drake Passage between Antarctica and South America opened, approximately 34 million years ago, allowing the Antarctic circumpolar current to form. This current, the strongest ocean current on Earth, thermally isolates Antarctica from the warmer ocean water to the north, preventing the heat exchange that would melt the ice. The opening of the Drake Passage, itself a product of plate tectonic movement, is therefore directly responsible for locking Antarctica into its frozen state and removing its land area from the habitable category. Now step back from the geology and examine what this geographic asymmetry has meant for life on Earth and for human civilization specifically, because the consequences are extraordinary in their scope and their depth. Biological diversity follows land area, and the concentration of land in the Northern Hemisphere has had profound effects on the evolution and distribution of species across geological time. The large continuous landmass of Eurasia, the largest single connected landmass on Earth, allowed species to disperse across enormous geographic ranges, encounter diverse environments, and evolve in the context of connections and exchanges that smaller, more isolated landmasses couldn't support. The Great American Interchange, which occurred when the Isthmus of Panama connected North and South America approximately 3 million years ago, provides a natural experiment in what happens when previously isolated land masses connect. Rapid faunal exchange, extinction of species unable to compete with new arrivals, and dramatic changes in the biological communities of both continents. The northern concentration of land also meant that when Homo sapiens began expanding out of Africa approximately 70,000 years ago, the primary dispersal routes led into land masses of enormous extent. The Eurasian supercontinent, which extended from Portugal in the west to the Pacific coast in the east, and eventually across the Bering Land Bridge into the Americas. The sheer geographic scale of the landmass available for human dispersal in the north contributed to the enormous diversity of human cultures, languages, and adaptations that developed across those territories. Jared Diamond's argument about continental axes, the observation that Eurasia's predominantly east-west orientation allowed crops, livestock, and technologies to spread across similar latitudes without crossing major climate barriers, while Africa's north-south orientation imposed the barrier of climate zone transitions on any south to north or north to south dispersal, is one of the most discussed applications of geographic determinism to human history, and it connects directly to the northern land concentration question. The east-west extent of Eurasia meant that domesticated crops developed in the Fertile Crescent could spread westward to Europe and eastward to India and China across latitudes with broadly similar day length and seasonal patterns. Wheat domesticated in the Near East could be grown in France, Spain, Pakistan, and eventually England. Different climates, but same latitude. Same day-length cues for germination and harvest. Same broad seasonal structure. This facilitated the spread of agricultural technology across an enormous geographic range within a few thousand years of initial domestication. In contrast, the domesticated crops of the Mexican highlands couldn't easily spread southward into the more tropical latitudes of Central America, or northward into the temperate latitudes of what is now the United States without crossing significant climate barriers that required crops to be readapted to new conditions. The north-south axis of the Americas imposed friction on agricultural dispersal that the east-west axis of Eurasia avoided. This is ultimately a consequence of the shape and orientation of the landmasses produced by the specific fragmentation pattern of Gondwana. The geometry of southern landmasses reflects their Gondwanan origin and drift trajectories, while the geometry of northern landmasses reflects their Laurasian origin. Ocean circulation is another dimension through which the northern land concentration has shaped Earth's climate system in ways that reverberate through human history. The distribution of landmasses determines where ocean currents can flow and where they are blocked, channeled, or deflected. The current configuration, with the Northern Hemisphere landmasses arranged around the Arctic Ocean and the Southern Hemisphere dominated by open water, produces a fundamentally asymmetric ocean circulation system. The Atlantic meridional, overturning circulation, which transports warm tropical water northward along the surface and returns cold deep water southward, is one of the most consequential circulation systems for human civilization. It's responsible for the anomalously mild climate of Western Europe relative to equivalent latitudes elsewhere. London sits at roughly the same latitude as Calgary, Canada, and the difference in their winter climates is largely attributable to the Gulf Stream and the broader Atlantic circulation that the geometry of surrounding land masses makes possible. The open Southern Ocean, unconstrained by land masses at the latitudes where the Antarctic circumpolar current flows, allows that current to move enormous volumes of water continuously around Antarctica without interruption. This circulation pattern draws cold, nutrient-rich water up from the deep ocean and distributes it through the surface Southern Ocean, producing one of the most productive marine ecosystems on Earth. The biological productivity of the Southern Ocean, the krill, the whales, the seabirds, is a direct consequence of the land-free geometry of the Southern Hemisphere that allows the circumpolar current to exist. The agricultural revolution, the single most consequential transformation in human history in terms of population, political organization, and technological development, occurred in the Northern Hemisphere. Not exclusively, but overwhelmingly. The primary centers of agricultural origin, the Fertile Crescent, the Yellow River Valley, the Indus Valley, Mesoamerica, the eastern United States, are all in the Northern Hemisphere, with the East African highlands and New Guinea as significant southern exceptions. The concentration of agricultural origins in the north reflects the concentration of the combination of conditions that facilitated domestication. Large wild populations of domesticable plant species, large animals suitable for domestication as livestock, and the climate patterns, predictable seasonality, adequate rainfall, appropriate temperature ranges, that both supported early agriculture and incentivized it as a survival strategy. The Northern Hemisphere, with its larger land area and greater diversity of biogeographic zones, simply offered more instances of those conditions converging. The animals domesticated in Eurasia, cattle, horses, sheep, goats, pigs, became foundational to human civilization in ways that had no equivalent in the Southern Hemisphere. The horse, domesticated on the Eurasian steppe approximately 6,000 years ago, transformed transportation, warfare, communication, and agricultural capacity across Eurasia and eventually the entire world. The absence of domesticable large animals in sub-Saharan Africa, Australia, and the southern cone of South America, a reflection of the different evolutionary histories of those fauna and the extinction events that removed large mammals from southern landmasses in ways that didn't occur in Eurasia, created a fundamental asymmetry in the technological toolkit available to civilizations developing in those regions. The population distribution that has resulted from these accumulated geographic advantages is striking even in the current era, when technology has theoretically reduced the dependence on natural geographic advantage. Approximately 90% of the world's human population lives in the Northern Hemisphere. That's not 6 billion out of 8 billion. It's closer to 7.2 billion out of 8 billion. The Southern Hemisphere, with its 32% share of land area, contains only about 10% of humanity. Sub-Saharan Africa, South America, Australia, and New Zealand together hold a fraction of the population of Asia alone. The reasons for this concentration are complex and deeply historical. They involve the agricultural and technological advantages that accrued to Northern Hemisphere civilizations over millennia, the disease ecology that accompanied European colonization of Southern Hemisphere territories, and the economic structures that developed from those historical advantages. But the ultimate backstory runs through the geology, the specific tectonic history that produced the current land distribution, which shaped which regions had access to domesticable crops and animals, which regions developed agricultural surplus that could support population growth and technological development, and which regions were isolated in ways that prevented the cross-cultural exchange that accelerates development. There's a philosophical dimension to all of this that's worth sitting with before the geology settles back into abstraction. The fragmentation pattern of Pangaea, the lines along which a supercontinent chose to break apart 200 million years before modern humans existed, determined, in meaningful causal chains, which civilizations had access to horses and which didn't, which agricultural zones could exchange crops across similar latitudes, and which faced climate barriers to dispersal, which populations encountered diseases that built immunity over millennia and which encountered them suddenly and devastatingly, and which regions developed the technological and organizational capacity to colonize others rather than being colonized. The land distribution that ancient humans were born into was not a neutral backdrop. It was an active determinant of the possibilities available to the civilizations that developed in different regions. The geographic lottery of which continent you were born on, determined ultimately by where tectonic plates carried your ancestors' territories, shaped your civilization's access to resources, its exposure to other civilizations, its agricultural potential, and its susceptibility to conquest. This doesn't mean geography is destiny in any deterministic absolute sense. Human agency, culture, historical contingencies, and the decisions of individuals all matter in ways that pure geographic determinism can't capture. But the framework within which all of that human agency operated was set by the tectonic history of the planet. And that history was profoundly, consequentially, unmistakably asymmetric. The geography classroom map deserves one more look before the question gets filed as answered. Stare at the northern cluster. Europe bleeding into Asia in an unbroken landmass stretching from Ireland to the Kamchatka Peninsula, North America sitting across the Atlantic with its own enormous extent, the whole northern hemisphere weighted with solid ground. Then look at the south. The ocean, the emptiness, the isolated land masses tapering toward a frozen pole. This is not what Earth always looked like. 300 million years ago, it looked completely different. 300 million years from now, it will look different again. Current projections suggest another supercontinent assembly, perhaps centered differently, perhaps with a different north-south balance than what exists today. The current configuration is a chapter, not the whole story. A product of geological events. The rifting of Pangaea along fracture lines, the drift trajectories of the resulting fragments, the opening of the Drake Passage that glaciated Antarctica, the mantle dynamics that continue pushing plates in their current directions. It is, like all things on geological timescales, temporary. But in the timescales that matter for human civilization, the timescales on which agricultural revolutions occur and empires rise and fall and technologies spread along latitude lines or don't, the northern concentration of land has been permanent enough to shape everything. Every crop that spread from the Fertile Crescent, every civilization that rose on the Eurasian steppe, every trade route that crossed the connected northern landmass, every population imbalance between the crowded north and the sparse south. All of it traces back, eventually, to the way a supercontinent chose to break apart, to the convection currents in a planetary mantle that human beings will never see and can only infer from seismic data, to a planet doing what planets do, indifferent to the consequences for the civilizations that would develop on its surface 200 million years later. Geography class never made it sound that interesting. It really should have.